This video is going to cover subsections 3.1 and 3.2. We'll begin with 3.1, likelihood functions for continuous variables. So one of the really important learning objectives of this course is for you all to be able to explain and understand the difference between a probability distribution, a probability density function, and a likelihood function. And that's what this particular slide focuses on. So let's begin with a probability distribution. And so this is the example right here of the little test that we did to determine gender numbers in Department X. And so remember what we did was we held pi constant at 0.5, n was equal to 30, and then what we did was we determined the probability of y for y values going from 0 to 30. So if you come up with our formula, n was constant, pi was constant, what we do is we plug y into the formula. What comes out is the probability of y. Probability of y. And remember, probability distribution, we're dealing with a discrete variable. And what you see on the y-axis is the probability of y. So you could say, okay, what's the probability if pi is equal to 0.5 and n is equal to 30? What's the probability of having 10 females in that sample? It would be read off the y-axis like that. So that was the probability distribution. What we did when we created the corresponding likelihood function was to, in a sense, flip things around. So up here, pi was constant, and the data, y, the number of successes, the number of females, that's what varied. Down here what we did was we held y constant. We held y constant at 22 because that's the number of females we found when we did our study. N, of course, was still 30, but now pi, the parameter pi, varied from 0 to 1. So there's our formula. We know n, but now, in contrast up here, pi was known. We plugged in different values of y. Down here, y is known, and we plug in different values of pi. So what we get is the likelihood function that is shown here. Okay, now let's look at this guy, the probability density function. So here we have a probability density function, and unlike a probability distribution, one of the differences between a probability density function and a probability distribution is that whereas a probability distribution deals with discrete variables, with a probability density function, we're thinking about continuous variables. And the example we showed in Chapter 1 was IQ. So here's the formula for a probability density function. And what have we got here? Well, we got pi, that's a constant, 3.14159.265. We've got a fixed value of sigma squares, and we know that sigma is equal to 15. Mu, that's a parameter. We know if it's IQ, it's equal to 100. But what varies is y. So we plug in different y values from 40 to 140, and what we get is probability density. Now, just to review, what's the difference between probability and probability density? Well, probability, again, if we go back here, we say, okay, what's the probability of getting 10 females? Well, there it is. But what we get on this y-axis is not a probability, rather a probability density. What's a probability density? Well, if we wanted to know the meaning of the probability density associated with an IQ value of 120, what that means is it's the probability of an individual lying between those two lines that straddle 120 divided by the distance between those two lines as the distance between those two lines approaches 0. So that's a probability density function. So what this subsection is really about is trying to say, okay, we saw here that we could go with a discrete variable. We could go from a probability distribution to a likelihood function. And so the question I'm posing is, can you go from a probability density function to a likelihood function just like you did here? And the answer is yes, but, and here's an explanation here, is why I'm not going to go through a process here. I'm not going to go through the process here that's equivalent to the process here because it's just really nasty complicated. Here it's pretty simple because only one thing varies, pi. Pi varies. But if we were thinking about converting this thing into a likelihood function, there'd be two components that we'd have to consider. We'd have to consider jointly mu and sigma, and that makes the math really nasty, so I'm not going to go into it. So last thing I want to point out before leaving this slide is that what we could potentially do, or at least think about, is drawing a line here, and above the line, what happens? Above the line, the parameters are constant. The parameters are given. So here, pi was equal to 0.5. Here, mu is equal to 100. Sigma is equal to 15. And what varies are the data. So number of females from 0 to 30, IQ from 40 to 140. Below the line, we flip that around. Below the line, the data is constant. So it would be 22 here, and we try different values of pi. And I can't really draw the diagram here because, like I said, it's complicated. But the basic idea is you could go out and you could measure a bunch of IQs, 110, 115, 95, etc. You could take that data, and on the basis of that data, you could determine jointly the likelihood of different values of sigma and sigma and mu, but it's really too complicated for this course. So that was section 3.1 that we just finished. Now what I want to do is move on to section 3.2, log likelihoods. So this is a likelihood function that we just saw. And in reality, we tend not to deal with likelihood functions. From a practical point of view, we're more likely to deal with log likelihood functions. And it's not a big difference. It's just that in this case, what goes on the y-axis is the likelihood, whereas on this axis, what appears is the log of that likelihood. So for example, if we consider this value here, 0.1630, if we were to take the natural log of that, what would we get? What we would get would be minus 1.8. So here would come across, that's minus 1.8 there. If we were to consider this value here of 0.5, if we were to take a log of 0.00545, what would that be equal to? That would be equal to approximately minus 5.2. So there's 0.5, pull that across, and it's about minus 5.2. So in the last video, we talked about some neat things we could do with likelihoods, and one was maximum likelihood estimation, and the second one was relative likelihoods. This slide focuses on some comments about maximum likelihood estimation. Next video is going to focus a little bit more on relative likelihoods. So just a few points about maximum likelihood estimation when we're thinking about likelihood functions and the log likelihood functions. First point is that regardless of whether you use a likelihood function or the log likelihood function, in terms of maximum likelihood estimation, you're going to get the same answer either way. So regardless, with this function, you get the likelihood maximized at 0.733. Here, with this function, you get the likelihood also maximized at 0.733. Now, how do we actually determine this value? Well, trust me, we don't just eyeball it. We don't just look at this curve and say, yeah, 0.733. Typically what we do is typically use the log likelihood function. And that's a lot more mathematically easier to work with. And again, I'm not going to go into the details because frankly I don't understand them. But basically, if you deal with a log likelihood function, it's easier to develop that function, take its derivative, and then using calculus, find out where it's maximized. Now, there may be some instances where it's really difficult to turn this log likelihood function into a formula that can be differentiated. In those cases, what we do is just use numerical brute force, the power of the computer. But regardless of whether it's using differential calculus or numerical methods, typically the log likelihood function is more likely to be used than the likelihood function. So we'll stop there.